Ever wondered how your favorite online services handle millions of users without skipping a beat? It's not magic. It's often the unsung hero called load balancing. In essence, a load balancer acts like a digital traffic cop, sitting in front of your servers and intelligently distributing incoming network traffic across multiple back-end machines. This isn't just about spreading the work, it's fundamentally about ensuring your system remains highly available and lightning fast, even under immense pressure. Think about it. Without a load balancer, a single server could become a bottleneck, or worse, a single point of failure, bringing down your entire application. By distributing the load, we prevent any one server from becoming overwhelmed, ensuring a smooth, responsive experience for every user. For those of us building ultra-scalable systems, understanding load balancing isn't just good practice, it's a foundational principle for resilience and performance. Today, we'll peel back the layers to see exactly how this crucial component works. Before we dive deeper, let's establish a few core concepts. First, clients don't directly connect to individual servers. They connect to a virtual IP, or VIP. This VIP is the single, stable entry point that your load balancer presents to the outside world. It's like the main entrance to a large building, regardless of which office you're ultimately visiting. Behind this VIP are your back-end servers. These are the actual machines running your application code and serving content. To ensure traffic only goes to healthy servers, load balancers continuously perform health checks. They ping servers, check ports, or even make specific API calls to confirm a server is alive and capable of handling requests. If a server fails a health check, it's temporarily taken out of rotation. Finally, session persistence, sometimes called sticky sessions, is crucial for applications that need a user to consistently interact with the same back-end server throughout their session. Imagine filling a shopping cart. You wouldn't want your items disappearing because your next request went to a different server. Session persistence ensures continuity. The how of traffic distribution largely depends on the chosen algorithm. The simplest is round robin, where requests are distributed sequentially, one after another, to each server in the pool. It's fair, but doesn't account for server capacity. A more intelligent approach is least connections, which directs new requests to the server with the fewest active connections, aiming to keep workloads balanced more dynamically. Then there's weighted load balancing, where you assign a weight to each server. More powerful or newer servers can receive a higher weight, meaning they get a larger proportion of traffic. Beyond algorithms, load balancers operate at different layers of the network stack. Layer 4 load balancers operate at the transport layer, forwarding traffic based on IP addresses and ports. They're fast and efficient, but dumb about application content. Layer 7 load balancers, conversely, operate at the application layer. They can inspect HTTP headers, cookies, and even URL paths, allowing for much more sophisticated routing decisions like directing requests for images to a specific set of servers or implementing A/B testing. Choosing the right algorithm and layer depends entirely on your application's specific needs and traffic patterns. Let's consider a real-world scenario, a global e-commerce platform. Imagine a major holiday sale, with traffic spiking by 10x in mere minutes. How do they cope? Load balancers are absolutely critical here. They handle those peak holiday traffic spikes by dynamically distributing millions of incoming requests across hundreds, if not thousands, of servers. Furthermore, for a global platform, load balancers distribute requests across global data centers. A user in Asia might be routed to a server in Singapore, while a user in Europe connects to one in Frankfurt, minimizing latency and improving response times. Crucially, they maintain user session integrity. Remember our shopping cart example? Layer 7 load balancers, often combined with sticky sessions, ensure that once you start browsing on a specific server, you stay there for the duration of your session, preventing frustrating data loss. This sophisticated orchestration ultimately ensures consistent performance worldwide, providing a seamless shopping experience no matter where the customer is or how high the traffic volume climbs. Without robust load balancing, such a platform would simply crumble under the pressure. So, we've covered the fundamentals, but load balancing isn't static, it's evolving rapidly. One major trend is service mesh integration. Technologies like Istio or Linkerd are bringing advanced traffic control, including load balancing, directly into the application layer, allowing for incredibly granular routing decisions between microservices. We're also seeing AI ML-driven optimization. Imagine load balancers that can predict traffic surges based on historical data and proactively scale resources or adjust distribution algorithms before a bottleneck even occurs. Edge load balancing is another significant shift, pushing traffic distribution closer to the user, often at CDN edge nodes, dramatically reducing latency for geographically dispersed users. Finally, with the rise of serverless and container orchestration platforms like Kubernetes, load balancing is becoming increasingly dynamic and ephemeral, tightly integrated into the orchestration layer itself. The core principles remain, but the tools and techniques are becoming more sophisticated, intelligent, and distributed. To truly master scalable systems, keep an eye on these evolving paradigms. The journey of optimizing traffic flow is continuous, and the future promises even greater efficiency and resilience.